chain rule. So just how we had the chain rule, we also are going to have the reverse chain rule. So essentially we just looked at the base forms, but we do have to remember that when we differentiate, we have to use the chain rule and multiply by the derivative of the function inside. So because we have to do that when we differentiate, that means that there's going to have to be like a matching thing to do when we are integrating. So therefore, to reverse this process when we're integrating, if there's a function inside the function, we need to make sure that the derivative of the function inside is already being multiplied on the outside before we can integrate the whole thing, which is called the reverse chain rule. Now, this sounds really complicated, but I will show you essentially like what this means with a few examples later on. But essentially, we need to make sure that the derivative of the function inside, so whatever the function inside is, we have to make sure that that derivative is already being multiplied on the outside. That sounds super complicated, but we will look at examples, so don't stress. So here it is, about looking at the reverse chain rule. Applies no matter what you're integrating. The same way the chain rule applies no matter what you're differentiating, reverse chain rule applies no matter what you're integrating. So essentially what that means here is that if we have f of x n, we have to make sure that we already have f dash x on the outside, and then we can do this integration. Okay, so that's going to be 1 over n plus 1 multiplied by fx n plus 1 plus c. Okay, so in order to be able to do the integration, we have to make sure that this fx, its derivative, is already on the outside. Okay, so same thing goes for all of our trig integration and our exponential integration as well. We have to make sure that this fx, its derivative, is already out here. So we've already got f dash x sine fx before we can integrate it to negative cos fx plus c. Same deal for your other two trig functions. You've got to make sure that your fx has its derivative out here before we can do anything with it. Same thing again with all of these. Okay, hopefully you do recognize this one in the middle as, I guess, the opposite of your log e or your ln. So if you've got the derivative on the top of the function and the fx on the bottom dx, then we're going to have ln fx plus c. Of course, we have to make sure that the top already has the integral, the derivative of the fx. Okay, same thing here. Got to make sure we've got the derivative of our f dash x out the front. Same thing, got to make sure we've got our derivative of our exponential out the front. Okay. Now this seems complicated and you might be thinking like, I don't know like how we can do that, how we can just like change things around, but we'll have a look at an example. So I'll give you guys a minute. This is a little bit tricky if you haven't done it already. So I'll give you guys a minute to have a go at this one by yourselves, and then we'll go through it together. Okay, so let's have a look at this one together. So hopefully you recognize that these two are very similar. And hopefully you're recognizing that it's looking like we might have to use this formula here. So the only thing is this numerator is not quite the denominator. Okay, so what we need to do here is not quite the derivative of the denominator, sorry. So what we need to do here is think about what do we need to do to the numerator in order to make it the derivative of the denominator. So first of all, with our denominator, we want to think about the derivative of that is going to be 2x plus 8. Okay, so from there, if we're thinking about the fact that the derivative of this is going to be 2x plus 8, then we need to think about that we need to multiply the numerator by 2 in order to have the derivative on top, okay? So if we make this on top 2x plus 8, we have just changed this function, okay? Now, just like anything, as long as we make things equal, then we can sort of change it how we want. So what we need to do on the outside of our function is then multiply the outside of the function by a half, okay? The reason that we're multiplying the outside of the function by a half is to account for the fact that we have multiplied the top by 2. Okay, so essentially multiplying a half by what we've already multiplied by 2 on the top essentially cancels that out. Okay, so whenever you're doing integration, if you need to change things around to sort of make them fit so you can do this, all you need to do is on the outside of your integral, account for what you have changed. Okay, so if you've multiplied the numerator by 2, multiply it by a half. Okay, if you have to divide something by 3, then on the outside you're going to be multiplying it, that sort of thing. From here, we then have exactly what we need to make this work. So we're going to end up with a half times ln of our denominator plus c. Okay, and that's all you have to do to use the reverse chain rule. Seems complicated, and then once you see an example, it starts to get a little bit more simple, and the more examples you do, the easier it'll become.